Hello world. Today we're going to talk about loss function. Note that this concept of loss function has been divided in two videos since I'll be giving a detailed explanation of loss function and how you can implement it and get more robust classifiers out of it. So let's get started. So in the part 1 we'll be talking about linear classifier to give you a more general intuition on why do you need loss function, and then we talk more upon loss function, and then we talk about multi-class SVM loss, and then to generalize the discussion we talk about underfitting and overfitting, bias and variance. So let's get started. So in the linear classifier, as you may have seen, what we do is we input an image in the classifier, and the whole thing which matters is this function over here. So f of x comma w, where x is the image. So consider x as an array of 32 by 3 numbers, and this 3 over here is a channel, red, green, blue, and this 32 by 32 is the length and width of the image. And what our classifier does is it's gonna input probabilities which tells us or indicate which class does it belong to. So in the case of CFAR10, as we have seen in the previous video of k nearest neighbors, there were 10 classes, and the classifier's job was to tell or output in probability which class does it belong to. So over here we have W. So W is the weights. So when we'll talk about deep learning, this W contains the weights of the neural network over here. So we're not going to talk more upon neural networks here. So this W is considered is weights, and it gathers much more weights from previous layers of neural network. So we initially randomly initialize it by in accordance with Gaussian distribution, and we split this array into this column vector over here, and then we add this bias term, and then we output a score. So whichever is highest gives an indication that our classifier is going to predict that this image belongs to this class over here. So what's loss function? So loss function, consider it as a function which tells us how good our classifier is performing on testing set. Of course, when we are gonna be testing a classifier, we want to make sure that it does well upon data which we haven't seen across. So we need to come up with a loss function which tells us how good a classifier is. So consider it is an algorithm that tells the classifier which types of error you care about. So initially we are going to be focusing upon multi-class SVM loss, which is a linear loss function, and consider it is a test of how good your classifier is. That's it for now. And so consider we've talked about this. So this images have been taken from CFAR10 dataset. So for the sake of simplicity, we are taking only 3 classes for consideration, and as you can see here, our classifier is outputting a probability over here. So whichever is in bold, which value is in bold, indicates that our classifier is telling us that this image belongs to that class. So here 3.2 is a dominant, 3.2 is in bold, which means our classifier has wrongly classified this image, because the dominant value over here is 5.1, and in the case of car it is telling us the right value, 4.9, and in the case of frog, our classifier has totally misinterpreted the whole thing. So its loss function is measure of how good our current classifier is, and we make use of something over this. So what we do is we compare the true value, and then we compare it with the value outputted by the classifier, and then we compare it over the whole training set, over the whole example. So given example x, y, where x is the image and y is the integer label, using the shorthand for the scores vector, the SVM loss has the following value. So what we do is, this is a true label over here, and this is the value which our classifier has predict it for us, and then we compute the value using this formula over here. So the minimum value of the SVM loss is going to be 0. As you can see over here, this function is going to be taking the maximum value. So the minimum value is 0 over here, and if the value which has been output by the classifier is too high, then the loss would be 0, which will be get back to later in this next slide. So we also make use of hinge loss. So this one over here, consider it as an safe boundary over here, and as we come closer to the right true predicted value, which is close to nearest value, our loss is going to decrease linearly, and this sy over here is just the score of the true class, and y-axis is the loss here. So as we come closer to x-axis, our loss is going to be 0. So we are going to be computing how. So what we do is we take the maximum values and we compare it with two classes. So here the value over here is 3.2 and 5.1 respectively. So we are going to compare 0 with the value sj minus sy plus 1. We are going to be computing that. So 5.1 minus 3.2. So it's always like the value of the next class minus the value which our classifier is telling us. So in this case 3.2. So 5.1 minus 3.2 plus 1, which is 0, which is 2.9. So the value of the function max 0 comma 2.9. So it's 2.9, and then we are going to be comparing the value of cat and frog. So in this case the value is in negative. So 0 is obviously greater than that, so it's going to be 0. So we compute loss function is 2.9, and similarly we compute this value for car also, and we are going to be computing that value for frog also. So in the case of car, our classifier has output the right probability right prediction. It's totally right. So 1.3 minus 4.9 plus 1, and the value is going to be 0, since the max of 0 comma negative number is going to be 0 only. And even if the value of car changes a little bit, it won't matter in this case, because since this term over here 4.9 is too dominant, when we are going to subtract that, it won't matter. And in this case of frog, the loss is too high. And what we do is, here we have 3 classes. We've taken 3 classes, so we sum over the whole training set. So in this case 3 examples, 3 classes are there, and then we are going to take sum of these 3 classes and then we divide it by 3. So we take the average of it. So I know this loss function is not much more robust, and we are going to be talking more upon log loss in the next part of this concept, loss function. And so this is a NumPy vectorized implementation. So always use vectorized implementation. I've talked. So why vectorization or implementation? Sorry, because the more for loops you're gonna use, the when you are gonna iterate over the whole loop, your algorithm is training part is gonna be slow. So always try to make use of vectorized implementation wherever possible. So this is a NumPy vectorized implementation. So first of all, as you can see, we have simply come up with this function with only 4 or 5 lines of code. So feel free to pause this video and have a look at this example over code function over there. And let's talk about underfitting. So I've made a separate whole video on bias variance, where I've talked more upon underfitting, overfitting. So to gain a more detailed intuition upon that, I've put the link in the description section below. So underfitting and overfitting are easy to understand but hard to master. So in this case, as you can see, suppose let's say these blue dots are from our training set, and when we test our classifier upon the training set, it does really well, it does a good job. But that's not what we want. We want the classifier to perform really good on the test sets or the data sets which we haven't seen across. And these green legends over here tells us that indicates that this data labels belong from test set. So as you can see, our classifier has totally misinterpreted it, and this curve over here is not doing the right job. And the better case would have been if we would have come across this linear line, because it's generalizing the whole labels really well. So that's where regularization comes into play. So what it's going to do is that your loss function may have access to polynomial functions also, and if you have access to that, then you're gonna be coming up with more complex decision boundaries, and you may be a victim of overfitting. I know that overfitting is a major concern when talking about deployment of classifiers, because what really matters to us most is that our classifier should perform really well on the test data sets, which we haven't seen across, and these green labels are a nice example of this. So what we do is we introduce a simple term. This lambda over here is called regularization parameter, so it should be simple. And even if your loss function has access to polynomial functions, we try to simplify this W matrix over here. So if lambda is large, then W, in order to compensate, we are gonna need to simplify W. So that's all which we have for part 1, and for coming up we will be talking more upon L1 regularization, L2 regularization, also called as Fourier norm, and we'll be talking about log loss, which is used in Kaggle competitions also. Thanks for watching this video. Please subscribe to stay up to date, and talk to the next one. Thank you.